to the CPS seminar. And so let me just briefly introduce our speaker today. So Ye Zhao is a assistant professor at Georgia Tech in mechanical engineering, where he leads the lab for intelligent decision and autonomous robots. And he's also affiliated with the IRIM Robotics Institute there, and also the Decision and Control Lab. His work is mostly on planning and decision-making algorithms of highly dynamic and contact-rich robots. And he's especially interested in challenging locomotion and manipulation problems with formal guarantees on robustness and autonomy. Before he joined Georgia Tech, he did his postdoc at Harvard, and he received his PhD in mechanical engineering from UT Austin. So let's welcome Ye Zhao to talk to us about his exciting work on robust planning and decision-making for safe locomotion. Take away.
Okay, all right. So let me share the screen. Okay, all right. So do you see the full screen? I assume
somehow I don't see, I was seeing it before, but somehow now I'm not looking at it. Yeah.
Not yet.
Oh, let me see. Oh, sorry. Let me do this. All right.
Yeah. Cool.
Okay. How about right now? Good?
Yeah.
Yeah.
Okay, all right. So good afternoon, everyone. So first, thanks very much, Feifei and Perdugi for inviting me for this seminar. And it's my great pleasure and honor to present at this USC Psychophysical System Seminar today. And I would like to take this time to talk about some robot locomotion planning and the decision-making works we have been pursuing now in our lab, and especially some fundamental challenges still existing in the locomotion community from my perspective. So nowadays, as we know, many world-renowned automobile companies have adopted highly automated production lines for their vehicle manufacturing process. And this is one example from Tesla assembly line for their Model S vehicle. As we can see, with current automation technologies, these industrial robots are almost as efficient as they can be nowadays. So almost every single component, like either giant ones or tiny pieces, can be assembled within a few seconds. And this has greatly relieved our human workload by performing this tedious task that cannot be automated previously. However, there's still huge room to make improvements. For example, in this scene, we can see humans and the machines are still separated by this safety fence, and we notice this do not enter warning sign there. In the long-term run, instead of replacing humans, robots should complement and augment the human capabilities. So nowadays, although we see a lot of powerful robot hardwares, the computational issues still prohibit these complex robot machines from operating in unstructured environments, maximizing the flexible production line efficiencies, or even interacting with humans safely. Not only industrial robots, but also in general, humanoid robots achieving more types of complex tasks. I think many people in this seminar probably have already seen these robots from Boston Dynamics and Agility Robotics. As we can see, these robots can demonstrate great agile and dynamic behaviors in these outdoor environments, indoor environments. However, there's still many fundamental challenges from either theoretical, computational, or experimental levels. So first of all, the dynamics are highly complex, so they are commonly high dimensional, nonlinear, and underactuated. And the practical issues always exist in the real systems, such as actuator dynamics, delays, friction, and etc. And many times the manipulation and the locomotion problems are still far away from achieving the performance like operating in cluttered environments, targeting contact-rich behaviors and human-level agility. And many planning and decision-making algorithms nowadays, I want to say still lack formal guarantees such as like robustness, safety, autonomy, and task variety, especially when this robot operates in the outdoor rough terrain or maybe partially observable environments. So it's very important for us to propose new computational tools and methods such that the robot can respond to unforeseen events and adapt to new environments at runtime. From a high-level perspective, a fundamental question we are interested in is what planning and decision-making algorithms do robots need to achieve agile, safe, robust, and collaborative behaviors, especially through contact. So in this talk, I'm going to talk about some recent task and planning frameworks for highly dynamic like locomotion, and in particular, present 3 unique angles to quantify robustness and reason about uncertainties. So I'm going to start with whole-body dynamic motion planning for our robots maneuver in this constraint environments and propose a certain robust metric to enable resilient contact locomotion decisions. And following on this direction, I will also talk about some task planning framework with this belief tracking, especially for safe locomotion in partially observable environments. And at the very end, I will discuss some contact-aware trajectory optimization method that can parameterize terrain uncertainties for robust cost function design and enhance risk-sensitive locomotion performance. Okay, so let's start with the locomotion, over the locomotion one. So to motivate this line of research, let's first take a look at a few real-life examples about dynamic or even extreme locomotions. So as we can see here, animals and humans are capable of achieving these incredible behaviors such as running, leaping, swinging, and climbing. And I think a key strategy underlying these dynamic behaviors is that they can appropriately use their legs and arms to interact with the cluttered environment and smartly take advantage of their natural dynamics. So these scenarios motivate us to question whether robots can achieve such level of agility and how to design appropriate planning algorithms and make robot contact decisions. So deviating from traditional bipedal like the locomotion, in this study, we are targeting more generalized multi-contact behaviors using all-limb contact. And the robot is expected to react to diverse environmental events by making sequential contact decisions. So we expect the task planner can satisfy all the required task specifications in this so-called probe-correct manner. And also I want to point out the locomotion scenarios in these constraint environments does have its real-world applications. For example, the Thailand's cave rescue a few years ago and the more recent DARPA subterranean challenge, although the current solutions mainly focus on the grounded or the aerial mobile robots. So to achieve these goals, a key question we should ask is how to intelligently compose and decompose these complex motions. So this motivates us to investigate template-based locomotion method. And in this case, we refer to real human motions, especially those observed in these parkour or gymnastic scenarios. So we extract the essential dynamics and model the abstract behaviors. In particular, in the field of dynamic locomotion, many people use these simplified models for planning control, for example, inverted pendulum model, hopping model, multi-contact model, and etc. So here our goal is to unify these template models using this sequential composition approach for planning. And it is essential to understand how to intelligently switch among different locomotion modes in response to diverse environmental events. So I would like to give a few typical examples about the contact decision if a robot want to maneuver in a constraint environment. First, the rough terrain is discretized into a set of symbolic values according to the terrain height, terrain geometry. So for example, if the next terrain height goes slightly upward, there could be multiple contact decisions that the robot can choose because this terrain is relatively easy to maneuver, so we can have multiple options. But on the other hand, if the terrain change is huge upward, then the robot has to make its hind arm and leg in contact such that the center of mass can gain a larger acceleration to step up. And similar things for the huge downward case, the robot has to make the full arm in contact to deaccelerate. And we can also model a few emergency environmental events. So for example, if there's a narrow passage in the environment, the robot is going to initiate a sliding mode, or maybe a human appears in the scene, the robot is going to come to a stop. Or maybe the terrain gets crashed, then the robot is going to grasp the ceiling wall and swing its body over this unsafe region. Or even if the ceiling wall is too high, then the robot can initiate a leaping motion here. So these are just a subset of environmental events and the robot actions we can take into account. And the designer can definitely propose more specifications, more environmental events as needed. But overall, in this situation, we can see the locomotion contact problem is essentially a switched system. And there are a series low-level locomotion modes we see on the left. And then the contact decision maker can control the switching signal P based on the science discrete environmental states. And then go through the synthesized control library, the execution, and finally the locomotion plant is going to output the locomotion keyframe states. And in this case, the keyframe state can be selected as the walking robot center of mass velocity and also the foot locations. So these are certain key parameters the designer can use, can design, okay? All right, so here we see there are a lot of parameters interweave with each other. It is essential to synthesize an automata for the contact decisions. And can we achieve that? The answer is yes, but not manually. So here I show one example about the synthesized automata for this contact problem. Here we can see how laborious it is to manually create this automata. And this automata can be more complex if we take into account more complex environmental events. We certainly need this formal method to automatically synthesize this contact decision maker for us, such that the robot can be responsive to various environmental events. So the way we frame this problem is to use temporal-logic-based formal method for the task specifications and the planar synthesis. And temporal-logic method have been widely used in the hardware, software verification. In the robotics field, it's mainly used for mobile robots motion planning, but it's still relatively underexplored in the dynamic lag locomotion community. And our lab have been pushing for this direction over the past 2 years. In particular, we follow a fragment of linear temporal logic formula named as a generalized reactive to one formula, which has the benefits of polynomial complexity. And basically by specifying the initial, translational, and goal propositions, we can formulate the following desired proposition phi in this so-called assume and guarantee form. So here basically phi q encodes the properties of the locomotion keyframe state, as I just mentioned, and phi e is the environment's assumption that encodes the knowledge about the allowable environmental behaviors, and phi s describe the correct behaviors of the overall system. So this formula basically tells us if phi q and phi e are satisfied, then the system is going to be guaranteed to behave in a correct manner. And here, our objective is to synthesize a contact planar switching protocol such that given a finite transition system TS and LTL specifications, we can synthesize a switching strategy gamma that only generates correct executions. So basically make the robots can successfully maneuver in this constraint environment. So for the state and the control in these LTL specifications, we literally have 4 sets of parameters. I probably won't go through all the details, but basically the environmental states is modeled as discrete states, including the terrain heights plus a few emergency events as the designer wants. The system actions is abstracted as the contact configurations as shown on the right. So these are just a few examples. So they're more like a system actions we present. Okay. And then the keyframe states represent the locomotion keyframe states, including the center of mass, apex velocity, and foot locations. And we also have a set locomotion modes, as I mentioned before, like the prismatic inverted pendulum model, pendulum model, multi-contact model, and etc. So let's take a look at one example. So this temporal-logic specification can be interpreted as it is always true that when a human appears in the scene, then the robot is going to take one of these 2 actions. So either do like hand-arm contact or do like a forearm contact. And it's going to also choose the corresponding keyframe states and the locomotion mode. Okay. So this is just one example. And again, I want to say the designer can follow the LTL syntax and to identify a rich set of safety and aliveness specifications as needed. And then given these LTL specifications, we solve a reactive synthesis problem by formulating this whole body planning problem as a 2-player game between the robots and its adversarial constraint environment. So the goal here is to synthesize a winning strategy such that the robots can win the game. And basically by using off-the-shelf solvers, either Tulip or Slacks, we can synthesize a cracked by construction automata. Here I show a fragment of this automata. We can see it incorporates all the states and actions I just mentioned in the previous slide. And basically for the problem in our study, this automata can have like more than 100 states, over 1,000 transitions, and some states have self-transitions, non-deterministic transitions. So this is definitely a fairly complex procedure, and this formal method help us to formulate, synthesize the decision maker such that we can make the locomotion mode switching and maneuver in these constraint environments. So let's take a look at how it works in the simulation. We basically integrate the high-level LTL-based task planner with the underlying phase-based locomotion planner. And the robots need to maneuver this complex environment through contact. And here we can see this environment includes not only rough terrain, but also multiple emergency environmental events. And for example, if a human appears in the scene, it's going to come to a stop, or if the terrain gets crashed, it's going to grasp the ceiling wall and swing its body over this unsafe region and have this kind of branchiation motions. So here, all the decisions are made according to the synthesized automata. And this task planner is generalizable to more locomotion behaviors. So in this case, we can see if the terrain and the ceiling wall get crashed simultaneously, the robot is going to initiate a leaping motion. Or if the terrain have a very narrow passage, it's going to slide through this constraint environment. So here we can see the synthesized high-level contact planner is going to govern multiple low-level locomotion motion planners and achieve these dynamic behaviors in this constraint environment. So here are some locomotion phase-based trajectories, especially in the robot's center of mass. And these trajectories are sequentially composed through these symbolic decisions. And different locomotion modes have different phase-based trajectory patterns, as we see on the top. And basically for dynamic locomotion planning, a very natural choice is to plan in the center of mass state space, which is a reduced order space characterizing the essential locomotion dynamics. That by properly switching the foot locations and also controlling the center of mass apex velocity, we can maintain the robot's center of mass trajectory are composed in this dynamic and safe fashion, okay? And as I mentioned previously, the correctness of this sequential composition is guaranteed, but only at the symbolic level. So any low-level model uncertainties, terrain perturbations, or external disturbance can break this formal guarantee quickly and cause failures at the low-level execution. So now the question becomes how we can reason about the robustness at the discrete level and devise robust planning strategies. To better understand the importance of this robustness, let's first see some preliminary results we have on our Cassie bipedal walking robots. To make sure the high-level locomotion planning algorithms successfully implemented on our Cassie robots, we have put a lot of effort on the sensing and the low-level control. So here we have 3 graduate students in the lab. They implement a joint level impedance controller synchronized with a high-level phase-space planner. So it did take quite a while to have all the planning, control, and the state estimation components well integrated. And here you see there's no visual perception yet. So the walking controller can successfully handle some terrain perturbations from the wood blocks, but it purely rely on the robustness of this default low-level controller. So recently we are actively moving towards this temporal-logic-based sequential composition such that the robot can respond to diverse environmental events, as I showed before, like going upstairs, ramp the terrain, or even when the terrain gets crashed. So I would like to come back to this robustness problem for a second. And here I want to highlight one observation we had during the experiments. And literally when my student Zhao Yuan poked the Cassie from the side at a specific time, Cassie cannot recover within 1 or 2 steps and then just step off the treadmill. And the camera didn't capture Zhao Yuan's face, but you can imagine how scared he felt about this push. So basically this failure case, I mean, certainly depends on the disturbance magnitude and at what walking phase this disturbance is applied and where it applied on the robots. There are a lot of different variations. But one thing we are sure is that locomotion planning without robustness reasoning is going to be failure prone and very fragile. So this motivated us to design a robust margin using analytical solutions of locomotion manifolds derived from this reduced order model, this inverted pendulum model, pendulum models. So here we show 2 consecutive walking steps, and each walking step has this valley type manifold. And then we derive tangent, cotangent manifolds to design this Riemannian space discretization. This is more advantageous than the traditional naive grid word discretization. So in this case, the abstraction is guaranteed to be consistent with the locomotion dynamics. And we design a set of robust margins around these nominal keyframe states and use the Riemannian manifold to quantify the robust margin radius, okay? Given this robust margin, we compute robust keyframe transitions through reachability analysis. So the procedure is follows. First, we identify a nominal keyframe transition designed by the high-level LTL-based symbolic planner for 2 consecutive walking steps. And then we expand this nominal transition cell by an epsilon expanded radius, and then take its neighborhood cells as alternative initial and goal keyframes, okay? And then we can compute the feasible transitions among these alternative keyframe pairs through the reachability analysis, which I'm going to talk about in the next slides. So basically, when the center of mass state is perturbed, then this robust transitions is going to search for an alternative keyframe pair transition for another successful run. And then we can generalize this robust transition to not only one type of locomotion mode, but a few others, and literally have this robust composition for more complex locomotion behaviors. And here we can see it go from inverted pendulum model to the pendulum model, and go back to inverted pendulum model and a few other multi-contact modes as well. Okay, and here I would like to point out one caveat. So basically, when the disturbance is very large, such that the state is perturbed out of the robust region, in this case, we cannot find a robust transition. So definitely our reachability analysis is disturbance dependent, although it is a powerful method to find robust transitions given bounded disturbance. All right. So our reachability analysis is used to compute robust keyframes, which is actually analogous to Dan Kotichek's work on this sequential composition. And this idea of sequential composition have been widely studied since last 80s, 90s. And there are seminal works from Dan's group, among few others. But I want to comment our sequential composition for this non-periodic keyframe state-based bipedal locomotion problem. It's still unsolved problem. And here the idea is that given initial and final keyframe reachable region of these two consecutive walking steps, our goal is to find a robust keyframe transition map from one walking step to the next one, and at the same time guarantee one walking step trajectory with this robust tube metric. And within this one walking step, a hybrid event for this contact switch should be taken into account when we compute these funnels. And if you need more information about this sequential composition idea, you can refer to this seminal paper at the bottom. So we believe this robust keyframe composition is a critical element for designing fast online replanning strategies, which are very important for safe and robust locomotions on our real system. And this is still an ongoing work, and we hope to have more results this year, so please stay tuned. All right, so to sum up, the takeaway message here is that for multi-contact locomotion problems, there are great potentials for exploiting high-level symbolic planning and the temporal-logic-based formal method to explore the discrete structure of the planning problems, and especially those induced by the contacting ones. And as to robustness, we would like to highlight we should reason about uncertainties not only at the continuous trajectory level, but also at the discrete decision-making level. And if you're interested in hybrid locomotion planning, I think we would like to emphasize the importance of unifying local locomotion and manipulation behaviors using sequential composition and make the robots react to diverse environmental events in a probable correct fashion. Okay. Okay, all right. So, okay, let me check the time. Okay, good. All right, so for this first locomotion work, I mainly assume the environmental information is fully known a priori, and this greatly simplify the robot environment interaction. I think in the real physical world, the robot's navigation problem often happens in these partially observable environments, and the robots may not have the full knowledge about the obstacle locations or maybe face a totally unknown physical world. So in this case, how can we solve these navigation problems in the 3D environments and guarantee multi-level safety? To start, I would like to point out a hearty debates these days still in the locomotion community. So it's really the lagged solution better than the wheels or the aerial components. I think different people is going to give us different answers. It's literally depends on what norm we care, right? So if we look at different metrics like energy efficiency, stability, agility, or maybe different kind of environment to navigate or different tasks to accomplish, we are going to get all different answers. especially in terms of mobility and agility. I think it has been well received that the lagged systems have a greater potential of maneuvering more complex terrains, either in the home environments, construction sites, or the warehouse. However, the underlying lagged locomotion dynamics often make the planning and the control problems very challenging. So even thinking about any navigation problems, the first thing for a lagged system to consider is how to balance safely and where to put the next foot location. So a central problem we are interested in is how to design planning strategies such that these lagged robots can locomote safely in these partially unknown environments, and at the same time accomplish these intricate teaming tasks like autonomous mobile robots. And there are multiple key considerations. So first, this locomotion problem need to consider not only balancing safety, but also navigation safety. For example, the robots should be able to avoid collisions with other obstacles or humans, and at the same time, it should plan the foot locations correctly, or even like grasp objects firmly. And another key component is the environments. So many times we have rough terrain, we have partially observable environments. The robots might only have a local field of view. And in this situation, how are we going to parameterize and abstract the environments? So do we choose like a fine or maybe coarse level abstraction? So all of these are going to give us different computational workloads and different planning capabilities. And the last but not the least is the robot task, right? So the robots, we want the robot to collaborate with other robots for some cooperative task, like delivering a package or maybe manipulate a box together with other robotic systems. To address this problem, we propose a hierarchical planning framework composed of task and motion planning layers. So the high-level task planner is composed of two sub-planners to handle task specifications at different abstraction levels, which I'm going to talk about in a minute. Essentially, this high-level task planner is going to generate a discrete locomotion action command to govern the global navigation task. And then the low-level motion planner is going to receive command from the high level and design these local safe walking motions in the 3D space and have the capability of maneuvering the rough terrain and steering the heading angles. So more specifically, as I mentioned earlier, our phase-based planner focuses on the center of mass dynamics. So by properly switching the foot locations and control the center of mass apex velocity, we can dynamically maintain the center of mass state within the safe region of the sagittal and the lateral state space shown on the top right. And on the other hand, at the high level, we aim for navigation safety such as collision avoidance and any other goal specifications such as like visit location A infinitely often or maybe other connectivity constraints for this collaborative robot task. And to really make this locomotion problem meet both locomotion safety and the navigation specifications, another question to ask is what type of environmental abstraction we should use, okay? And what is the appropriate granularity a discretized environment should have. So for example, if the granularity is too small, the total number of this discrete cell is going to be too large and make the computational part intractable. But if we choose the granularity too large, like very coarse cells, then it's very difficult to reason about the decision of each individual walking steps for the locomotion problem. To address this, we propose a two-level abstraction of the environments. So at the coarse level abstraction, we have this large cell discretization of the environments. So the circles here represent the robots and the dynamic obstacle, and the red box represent the static obstacle like walls. Gray and black boxes are related to the obstacle belief tracking. I'm going to talk about in a minute. And basically for each coarse cell, it has a fine level abstraction with much smaller granularity that allow the walking robots to make decisions on the foot placements and heading angle change. And basically, to navigate one course cell, the lagged robots is going to take multiple walking steps at the fine level cell. And in this case, we can design and guarantee both local walking decisions and the global navigation specifications. Okay. So given this two-level environment abstraction, now we have another another problem. So if we take a close look at the robots and the dynamic obstacle locations in this course level cell, we can realize that the robots might not perceive the obstacle locations because of this visual obstructions from the walls or maybe other static obstacles. So in this case, how can the robots make decisions on where to go next without full knowledge of the obstacle? And I think a natural direction is to reason about the environmental observability. So to allow navigation in a partially observable environment, we employ a belief abstraction and use this to track possible obstacle locations when the obstacle is out of the sight. So the abstraction here is designed by partitioning regions of the environment into sets of discrete states, constructing the belief regions. And basically, by dynamically tracking the Boolean index of this belief region set, we are able to track not only the possible obstacle locations in these non-visible regions, but also determine which non-visible regions that is going to be obstacle-free. To evaluate this belief tracking performance, we construct this open world environments. The walking robot is required to visit the pickup location at the upper level and move the destination at the lower level, at the same time avoiding collisions with the obstacle, which is the mobile robots in this case. And here the belief abstraction of the environment is updated online based on its local view of the field. And here we see the light gray cell represents the belief region of possible obstacle locations, and the dark gray cell represents the non-visible regions that are going to be obstacle-free. And these days, we also targeting a generalization to handle multiple dynamic obstacles, for example, two mobile robot obstacles, or maybe three, or maybe more than that. So how can we build a joint belief abstraction of the obstacles without significant computational load increase? So this is another ongoing work. This semester, we moving towards to more complex scenarios and targets a scalable, safe, hierarchical mission and task planning framework. And we are especially interested in this last mile delivery problem and explore collaborative robot tasks, especially involving lagged aerial and manipulation robots. So one scenario we are studying now is how Cassie can team up with fleet quadrotors and form this leader and follower subteam for the package delivery. And more specifically, we are looking at the long horizon robot tasks, such as a KUKA arm going to store the object into the box. And after that, Cassie robot is going to pick it up and deliver it to a destination location downstairs. And the key research questions that we are addressing includes how to make contact decisions with the manipulated object and how to avoid collisions with the dynamic obstacle in these environments. And from the high level mission planning perspective, we are also looking at problems on like how to design decomposition algorithms such that the multi-agent system can be decomposed into multiple robot systems while guaranteeing the global task specifications. Okay, all right. So also motivated by this collaborative robot task, we are exploring multi-contact locomotion and manipulation task planning. So how to design optimal task allocation strategies for this object-centric contact planning. And we are investigating signal temporal logic to specify local manipulation task specifications and how to transform these signal temporal logic specifications into a mixed integer program for this multi-contact planning, which is going to be modeled as a virtual linkage model inspired from this grasping community. And I think just for the sake of time, I would be happy to talk about more details offline if you're interested. Okay, so so how much time I have? I just want to make sure we are good on time.
I think with yoga, like 15 minutes.
15 minutes, okay. Okay, good. So I will briefly talk about the last direction, especially on the robust trajectory optimization and how to handle contact problems. So for the previous problems, all the contact part is treated as the discrete decisions, and we ignore a lot of frictional contact dynamics details. But in reality, these contact problems could be very complex and often make the planning and control algorithms difficult to solve. So I think I would like to use this one slide to motivate a little bit about why the contact problem is challenging. And I think a fundamental reason is due to the discontinuity in dynamics. So, and also the contact behavior is a binary outcome. So it's either in contact or not. And these combinatorial contact possibilities might become computationally intractable when the total number of potential contact increase a lot. So for example, in this first simulation, when there are a lot of boxes collapse, it's impossible to specify the contact interaction one by one. So I think from our perspective, a key factor that makes this traditional trajectory planning control become brittle is this uncertainty. And here in these manipulation examples, we can see there are various sources of uncertainties like the object, the geometry, the pose, and the friction properties. And at the same time, this contact switch mismatch can lead to a catastrophe. And there are a lot of related work in this hybrid planning community, like reasoning about the phase-based and the time-based strategy. And for trajectory optimization, especially solving large-scale nonlinear optimization, it's going to involve a lot of numerical problems, and all of these are going to affect the contact performance. So I think I would like to skip a few slides. So basically, this is talking about, well, we start with the general optimal control problems, and there are many ways to solve these optimal control problems, either like multiple shooting, direct method, or DDP. But the missing part is actually the contact constraints. So what we do is basically add these contact constraints into this optimization problem, and then we can add a series of contact force decisions as the decision variables, and we solve this so-called contact implicit trajectory optimization. And along this work, there are several seminal works in this area, like a post contact implicit trajectory optimization and the Mandarch approach on this contact invariant optimization. And the core idea is to solve this large scale optimization that can automatically figure out the contact forces. But there's one problem for this type of research. Basically, during the implementation, people realize that the optimization sometimes can become brittle due to the contact uncertainties, like those from the terrain geometries or the terrain coefficient. So in this work, we are interested in reasoning about contact uncertainties. And the question is how we can model these contact uncertainties when we don't have the full knowledge about the terrain coefficient or geometry, and how we can design robust motion plans. So the way we frame this problem is is to parameterize the friction coefficient and terrain height uncertainty through this Gaussian distribution. And we replace the deterministic contact constraints by an expected residual minimization term, which is called the ERM cost. And it basically minimizes this expected residual of the LCP per duct. And by inducing this ERM cost into the objective function, we can enforce the contact constraints in a probabilistic sense while taking into account the parameterized contact uncertainties. And by some mathematical manipulations, we can also realize that this ERM cost is equivalent to the mean residual plus the variance term, which can be interpreted as a risk-sensitive formulation. And basically, by selecting specific signs of this variance term, we can derive the risk-seeking or the risk-averse strategies as needed. So we evaluated this robust trajectory optimization on simple horizontal part and the single-legged hopper examples. Basically, given different terrain uncertainties, we observe different locomotion behaviors. And the trajectory optimization with larger terrain uncertainties generates the locomotion gates with relatively large foot clearance. Because the robot doesn't have a perfect knowledge about the terrain and is trying to stay away from the terrain as much as they can. And basically being away from the terrain can give us a smaller ERM cost that parameterizes this cost uncertainty. And this work is significant because it's really the first time that these contact uncertainties are explicitly parameterized and incorporated into this contact-aware trajectory optimization. And it opens the opportunities for leveraging this contact-rich trajectory optimization to design motions, especially for robots maneuvering in these outdoor and known terrains. And here are some directions we would like to move forward, like including exploring more complex terrain geometry, deformable contact, or even closing the loop between planning and the terrain estimation. I would be happy to talk more if you are interested in this part. So maybe the last part I would like to just briefly mention is a trajectory optimization for distributed like full body dynamics consensus. So for example, if we take Cassie robot, for example, we can see there are lots of constraints in this case, like whole body dynamics constraints, centroidal dynamics constraints, contact constraints, etc. Many existing algorithms usually solve this optimization with all constraints simultaneously, which make this algorithm often suffers from convergence problem and numerical issues. So our motivation is really to decompose these constraints into multiple blocks and solve them in a distributed fashion. So along this direction, we solve this full body optimization by employing this distributed optimization approach named ADMIM. And we use this consensus method to achieve the full body optimization. And the core idea is really to decompose this large scale, highly non-linear program into multiple subproblems and iteratively solve this augmented Lagrangian optimization. So I will skip some details here. I'm going to skip this as well. We also have work on this PDDL-based AI planning for long horizon manipulation. We are also interested in designing this new Cassie foods sensor pad for the terrain classification and for the contact sensing, so we can design better control and motion planning strategies when these robots really go to very complex terrains. And this is a new project. We are doing fast planning perception for autonomous navigation. We'll skip it. So I think the very last thoughts before I close this seminar is really, I think over the next 5 to 10 years, we're going to see a lot of lagged system really showing up in our daily life and maybe teaming up with other different kind of robots and accompanying our humans for outdoor environments or maybe other disaster response. So hopefully we can really see this day happening sooner than later. So with that, I'm going to stop and I will be happy to take questions if we still have a few minutes.
Yeah, thanks for the very exciting talk. A lot of very cool work here. We do have a question in the chat. So the QA, let's see. So when a robot encounters obstacles, when considering how to avoid obstacles, will it consider which way is better to save energy?
Okay, let me switch back. To see. All right, sorry. Okay, all right. Sorry, I'm sorry. Can you repeat the question?
Yeah, so it's asking about the energy efficiency consideration, especially during the robot obstacle avoidance. So the question is, when the robot encounters obstacles, when considering how to avoid them, will it consider which way might be better in terms of saving energy?
Yeah, I think that's a great question, and especially in terms of avoiding collisions with the obstacle, I think we can reason about it at two levels, right? So one is kind of the local level, like the short horizon, really when the walking robots already stepping out the obstacles, so how it can take advantage of this locomotion dynamics to dynamically maneuver this, and it's going to have generate maybe energy efficient locomotion gates. And this is the first stage. And another stage is really on the long-term run, right? If the robots maneuver in a unknown or maybe partially known environments, there may be obstacles a few meters away from the robots. And in this case, the robots need to be able to select a different walking paths, right? So maybe from the high level. And in this case, there could be energy efficiency considerations being taken into account. Yes. So from the formal method I presented, we haven't taken into account a lot of energy efficiency, but I think these are definitely some norms we can take into account into this high-level optimization problem. And for the trajectory optimization I presented at the very end, this energy efficiency is basically the control term, right? This U square term, and we do take into account this control effort consumed by this walking robot. Yeah, but in terms of obstacle, it really depends on what type of obstacle we are reasoning about, the local ones or maybe the global ones. Yeah, so.
Yeah, thanks. There's a second question here. It's asking about, I think, sensors and how you're integrating them to improve the robot's ability. So the question is like this: LiDAR and cameras can improve robot's ability and dynamic performance, such as Tesla Autopilot or iRobot Roomba. What kind of other new technologies are going on, ongoing development to improve the robot ability related to your work?
Mm-hmm. Yeah. Okay. Yeah. I think from the sensing perspective, I really want to comment, especially for this select system, is very different from other like mobile robots, which kind of move around relatively stable on the level ground. And especially when these robots go to walking robots go to outdoor environments, rough terrain, there are going to be a lot of dynamics happening at the low level. And then I think whatever the high level perceptions, data estimation method we use, we should take into account this underlying dynamics. And if we do slab thing, so how this like walking dynamics is going to affect the performance of your localization, of your state estimation, of your center of mass. I think this is definitely a key question. I think this is the kind of the new directions a lot of people looking at these days, and even like companies like Boston Dynamics, they do this autonomous navigation, both indoor, outdoor. The sensing part is I think is a key part. Yes, and we are taking a look at a lot of techniques, methodologies from autonomous driving, mobile robot community. I think that's definitely helped a lot for locomotion people to explore this area. Yeah, I'm not sure this will address your question about the sensing technology.
I think that's a great answer. Yeah. We have another question here. Thank you for your nice talk. Could you comment on what is a good concept or thinking of safety if the environment is unknown?
Yeah, that's a hard question. So if the I guess you're asking if the environment is is completely unknown, right? So in this case, it's literally the robot is walking in a kind of like a dark world, and well, it can still walk, but I think what's we want to claim is basically we should have some like a sensing information, have some knowledge about the environment, but maybe it's not perfect. But if there's nothing we know about the environment, I think the safety is pretty much just rely on, well, the kind of the defaults like controller you have. Maybe when you hit the obstacles, you are robust enough to recover. For the experiment I just showed, we don't have the perception yet. It can maneuver over some rough terrain, but this, I think, yeah, good luck. I think this, if it's safe, I think it's safe. But I think, yeah, from the perception environment to perception level, I think there's not too much we can reason about. But safety for the dynamic locomotion dynamics, that's for sure. I think planning control level, I think these are the topics I think a lot of people trying to reason about, and I still think this formal method is a good way to accomplish very complex dynamic locomotion behaviors, and also guarantee safety. Yeah.
I have a quick question. I think we are exceeding the time, so I try to be concerned to be fast. So I was just wondering, so you indeed show two kind of approaches to formal methods, right? In the first problem, more the, let's say, abstractions of LTL together with the lower level control in with the funnels and with the robust. While I think in the second project or so, you were start to looking at even proposing, right, STL with uses of optimization, MILP, some kind of model predictive control somehow approach on this. So I was wondering, is there, so are you planning to shift, or there are actually important elements of the problem, of the physics, that motivate one or the others, or?
Okay, so if I understand correctly, you're asking the motivation comes from the physics, or maybe more from the methodology?
From the methodology or from the mathematics, right? Going to LTL and then lower level control. So going from STL and then model predictive with MILP, or? Yeah,
I think I want to say we are more motivated from the, I think from the underlying physics, the locomotion problems, and this optimization, this formal method, LTL method. I think these are very powerful tools we can take and we can leverage to solve our locomotion problems. Because traditionally, I think a lot of locomotion people they didn't take a look at I think this formal method to solve, like, well, I think like this LTL based formal method to solve locomotion problems. But I think these are very powerful methodologies, and it can really help us to solve our locomotion challenges. And yeah, I think that's kind of our motivation. And another thing I think maybe comments from the methodology part. I think, well, a lot of people focus on the formal method, more theoretical developments. Many times, I think when they write papers and they publish their results, they maybe often use like this simple 2D grid word mobile robot examples. I think I think it's the first step. But if we really want to scale all the methodologies to high dimensional robotic system, I think looking at robotics problems definitely, like this lag locomotion problem is a high dimensional under activities. I think it's more challenging robotics problems to take a look at.
Yeah, indeed, and it's impressive, right? The results that you are achieving by deploying actually on some platforms.
That's right. Yes.
Just one last quick question. I was also interested into the compositionality of your distributed optimization.
Mm-hmm.
I was wondering, right, in the way you decompose the problem, applying consensus and so on, whether also there are decomposition strategies that are based on the physics, or whether you are looking at the also there mostly at the computational hardness or the just model of the constraints. And
This is a very nice question. I think this, like when the students like tune these optimization problems, many times for this distributed optimization algorithms, how to make it converge. I think that's kind of the key part in the. I want to say I think it's both. Like many times the convergence rates of these optimization algorithms depends on what kind of physical constraint we have and how we handle these physical constraints, like introducing different optimization techniques and tricks to make the converge faster. And at the same time, I think fundamental methodologies from this ADMM distributed optimization, different updating sequence among different blocks, this definitely help us a lot. And I think many times getting these algorithms converge, I think this is literally the key part in the, I want to say both, yes, it's both of them are very important, yeah.
I expect you try to use some heuristics that.
It's more heuristics, and the students need to understand the problem. So he need to understand how this physical constraint affects the convergence, the numerical stability. So there's some like heuristics and insights embedded in solving this problem.
Yeah, actually, just following really quickly upon the connection between, the high-level reduced order model to the physical, actual implementation of these. You talk about this nice, sequential composition of different, very reduced order models, right, and different templates. But in reality, they may have different discrepancy between how the dynamics is modeled to how actual dynamics in the physical, as you said, due to the physical interactions and perturbations. So how do you have any comments, just like at a high level on, whether these like a low level physics interaction will feedback to influence your decision, those like high level abstract decisions when selecting the switching between these different templates? Or do you think you can separate, you can separate them and just like work on both sides independently?
Yeah. I think so far, well, there's no like a golden metric yet. It's really problem dependent. I think many people will use this reduced order model at a high level, but when they really execute it at the low level controller, there's like a model discrepancy, and there are also a lot of uncertainties at the low level. So this all kind of break the assumption of formal guarantees you get from the high level. So I think replanning is maybe a good strategy. I mean, this is more from the practical perspective. Like if you can detect this error, or maybe your assumption is broken at the low level, then you can send a signal to the high level and then do the replanning at runtime. I think that could be like practically speaking, this is a very useful strategy and powerful strategy. And I do see people like exploring kind of when they handle the full body dynamics, they kind of embed this reduced order model into their optimization problems. So when they solve the full body dynamics, they already incorporate these templates models. But I think there's still a lot of computational discussions. It's very slow. Many times it's a little bit far away from real time. But if we use reduced order model, template model, we can plan things very fast. So I think this kind of like a different like strategies people have been actively looking at. Yeah. So I think how to guarantee this model consistency across different levels. I think this is still active research problem to be solved. Yeah.
Yeah, indeed, it is a kind of a holy grail also for formal methods, right?
Yeah.
Nice abstractions and then guarantees the transition between them, like some kind of vertical contracts, between the top level and the lower level, essentially. That's great. Actually, it's very interesting also this discussion on robustness at the two layers, like at the level of the funnels and at the level of the LTL as well, that you are trying to use. Yeah.
All right, very cool talk. So I think we don't have any more questions in the Q&A. So probably let's thank our speaker. And yeah, I also have more questions, so I actually might send you additional questions, offline. But yeah, it's a great talk. Really, really glad to have you here today. So
yeah, thank you, everyone. If you have questions, feel free to send me email, and we have the website on the last slide, and we'll be happy to talk more. Thank you, everyone.
thanks.